Hi all, today we discuss section 4. This section deals with the properties of groups. This group is an algebraic structure. This is the definition. A group G star, this is an algebraic structure. G is a set and together with a binary operation. This is a set G. A group G star is a set G closed under binary operation star. So this star is a binary operation. Closed under binary operation star means the star is a function from G cross G to G. That is the definition of binary operation, such that following axioms are satisfied. What are the axioms? The first axiom is denoted by G1. That is for all a comma b comma for all a comma b comma c belongs to G, we have a star b star c equal to a star b star c. Okay, you might have remember this statement or equation. So this is the property of associativity. Okay, so simply you can say that G1 is nothing but G1 says that star is associative. Okay, associativity of associative. This binary operation is associative. This is the first axiom, and in the second axiom we establish the existence of identity element. Okay, that means if you have the second axiom G2, then there is an element. There is an element E in G such that for all x belongs to G. This is the definition of identity element. For all x belongs to G, we have E star x equal to x star E, that is equal to x for all x. Okay, so this axiom can be remembered as identity, existence of identity. Okay, existence of identity element. And finally we have the third axiom, that is G3. This establishes the existence of inverse element for each of the elements of G. That means, what do you mean by inverse? So corresponding to any element, if you choose any corresponding to any element, each element A belongs to G, we can find another element. There is an element, we call it as A prime, such that A star A prime, that is equal to A prime star A, which is equal to E. Okay, so this A prime is called the inverse of A. Okay, so A prime is the inverse of A. So in order to define the inverse of an element A, we need to define identity element first. So the order of these axioms are very important. So first you define associativity and you establish the existence of identity, then only you can get the existence of inverse. Okay, inverse element. So if every element of G has inverse, then we can say that G3 is satisfied. Okay, so if a algebraic structure G comma star, or star is a binary operation, that is the star is the binary operation is closed under this G is closed under binary operation, then if G satisfies these three conditions, we call such a binary structure is called groups. Okay, so we now onwards we are discussing the properties and some existence of groups throughout this abstract algebra. For example, we consider real numbers under addition. That is the simplest example. if you consider the algebraic structure R under addition, usual addition, so we can say that this plus is a function from R cross R to R. We already established this is a function from R cross R to R, so which shows that what is the meaning of this? Plus is this R is closed under addition. Okay, so that is the meaning of this. And we have to verify the first axiom. We know that A plus B plus C these are the usual additions, so that is same as A plus B plus C for all A comma B comma C belongs to R. So which this establishes G1. That is the first axiom, the associativity of this addition. And the second axiom is the establishment of the second axiom establishes the existence of identity element. So that is nothing but 0. Here A plus 0 is A, that is equal to 0 plus A for all A belongs to R. Then we can say that 0 is the identity element of R. Since the 0 belongs to R, then R contains identity element. For the final axiom, we have for any A belongs to R, we can get minus A. Negative number is also an element of R, such that A plus minus A gives 0, which is same as minus A plus A. So this establishes the existence of inverse element for each of A belongs to this R. Okay, so this shows that R under addition is an example of group. Okay, now there are several examples are discussed in the textbook. Some of the examples can be discussed here. After that, you can go through the other examples in the textbook. And other example is the second example is set of all integers. Set of all integers is denoted by Z under addition. Okay, Z under addition is also a group, so you can easily verify that sum of two integers is integer is again an integer. So we can say that this plus is a function from Z cross Z to Z itself. So this is the existence of the binary operation. And the second one is the same thing, A plus B plus C. A plus B plus C for any any three integers, we have this result, the same as A plus B plus C. Therefore, we can say that this plus is associative in Z as well. Now we have 0 plus A gives A plus 0 gives 0 itself, sorry, A itself for all A belongs to Z. So this establishes the existence of identity. And finally, if A is an integer, then we know that minus A is also an integer. Okay, so A plus minus A gives minus A plus A, which is equal to 0. So this establishes the existence of inverse element for each of the elements of Z. Okay, but if you consider positive integers, that is denoted by Z plus, set of all positive integers under addition, this is not a group. Okay, so this is a non-example. Why it is not a group? We know that 0 does not belong to this. When this is a binary structure, this is a plus is closed under this addition. That means sum of any two positive integer is again positive integer. But we cannot get identity element in this collection. Okay, this does not belong to plus or sorry, this is not 0. We cannot get any identity element. 0 is not an element of this, but E cannot be in Z plus. That means if we choose any element of Z plus, that cannot act as an identity in Z plus. Okay, so that is the idea. Now we have a set of all non-negative integers, that is Z plus union singleton Z0. This structure is not a group as well, because even though this contains identity element, the inverse is not there. If you choose one belongs to Z plus, you cannot find an element. There is no A such that 1 plus A equal to 0. Okay, since 0 is identity element, you cannot expect any element A belongs to this Z plus, because if there exists such A, then A will be -1, and -1 is not an element of this Z plus. Therefore, Z plus union 0. Therefore, Z plus union 0 is not a group. So these two are non-examples. There are several examples and non-examples are discussed in the textbook. So please go through it. Next we have another definition, commutativity of a group structure. That means a group G along with a binary operation star is abelian. So this is due to the famous mathematician Abel. So this is read as abelian. A group G is abelian if its binary operation is commutative. Okay, that means if you have a groups a G comma star, and it satisfies in order to be a group, in order to this G's in order to get this G as a group, we need to verify the three axioms along with this binary operation star. Apart from that, we need to verify the commutativity of that. Commutativity of star, that means A star B is equal to B star A for all A comma B belongs to G. Okay, if this is also true, then we can say that this G is an abelian group. Okay, that means A star B is equal to B star A for every A comma B. We already discussed what is the commutative property of a binary operation. So in a group, apart from the axioms of group, that group satisfies the commutativity of that binary operation. In that case, we call that group as abelian group. Okay, for example, we can take R plus itself. R plus is an abelian group because A plus B, we already seen that this is a group, and we can see A plus B is equal to B plus A for every A comma B. So this is an example for abelian group. And we have Z under addition, that is also an abelian group. But if you consider set of all n by n matrices n, m and r, we already discussed what is the symbol stands for. This denotes the set of all n by n matrices over R. That means a set of all n by n matrices whose entries from this real numbers R. Okay, if you consider this under multiplication, this form a group, matrix set of all n by n matrices under matrix multiplication. We know that any two product of any two n by n matrices is again m and r for all A comma B belongs to m and r. So we have this matrix multiplication is a binary operation on this m and r, and if we have identity matrix, then we can get A times I is equal to I times A is equal to A for all A belongs to m and r, so which establishes the existence of identity. And if we have this m and r with we have there is no inverse element for this collection, because if A belongs to m and r, we cannot expect A inverse, or we cannot expect a B such that A times B is equal to I. Okay, so this is a question. So we if we take all of this m and r under multiplication, never be a group. Okay, so there are some groups which is not commutative. Okay, so this is not a commutative group, this is not itself a group, but if you collect some elements of this, okay, so if we choose a set A with the property that A belongs to m and r such that determinant of A not equal to 0, this is set of all non-singular matrices. Non-singular matrix means whose determinant is not equal to 0, and this is denoted by the symbol GLNR. That means GLNR is a subset of M and R consisting of the non-singular matrices. If this is the case, we can get if A times B, we know that determinant of A times B is equal to determinant of A into determinant of B. If determinant of A not equal to 0, determinant of B not equal to 0, then we can get the product is not equal to 0. Then if we choose any two arbitrary element, A comma B belongs to this G, L and R, then we have AB, the product is itself in G, L and R. Okay, which shows that this multiplication is a binary operation. Similarly, we know that identity element, that is a determinant of identity element is 1, then this belongs to G, L and R. But here we have inverses for each of these elements. Okay, since determinant of A not equal to 0 implies that that you can define B is equal to 1 by determinant into adjoint A. Okay, so if we choose any A belongs to G, L and R, then you can get A into B is equal to identity, which is equal to B into A. This shows that this is a G, L and R is a group. Okay, in this at the same time M and R is not a group. Okay, M and R is not a group under multiplication, matrix multiplication. This M and R can be a group with the usual matrix addition. Okay, but this G, L and R can be considered as a group as well. But here we know that A times B need not equal to B times A in general. If A times B is equal to I, then that will be same as B minus B times A. But in general, AB not equal to BA in GL and R. So this shows that GL and R is a group, but it is not a commutative group. Okay, so this is a non-example for commutative group, or this is not a commutative group or abelian group.